So let me show you also what to do if you have a little bit more complicated task. For example, if you need to compare mean of several samples, or maybe median of several samples, or compute any other more complicated statistics. So in this case, I will try to compare two samples came from two different populations, but without using, for example, a t-test, or without using non-parametric approach like Mann-Whitney test. Again, I have two samples. You can see A and B here, right? And then I combine them together into one long vector. Then I create the labels. So for example, all these values will have label A, right? So you can see I repeat A 7 times. I did it also in the non-parametric approach when I presented the methods for non-parametric approach. And then I also create labels for this one, right? So we'll have a data frame which will have two values, X and G. And then the first value for X will be 10.6 and G will be A, then and so on and so forth. I recommend you to run this code in your studio and see how the data frame looks like. But this is my data frame. So in this case, I have 14 rows in 14 rows and 2 columns, right? Now, how to compute confidence interval for the difference of means? So I need to compute difference of mean for A and difference of means for B, right? There are several ways to do that. I'll show you one of the ways. So this is my function. Look, the function looks similar to what we had before, right? So you have data and you have indices. But now you should remember, data is not a vector. It's this data frame. So it's 2 columns, right? It's 2 columns. Here I have values, here I have values, and here I have groups, right? And therefore int, it's indices of rows. It's not indices of values, it's indices of rows that I need to make a subset for. Now, this is what I'm doing, right? So first, I take only subset of rows and the first column. So it will be a subset of values in the first column, and I keep it in X. Then I take also the same rows, but the second column and keep it in G, right? So it will be these ones. Then I say compute mean for values in X, already subset, but only which corresponds to the letter A in G, right? So it will take only values from sample A, then do the same for the B, right? So here I will have average value for the subsample, for the random subsample for group A, and here I will have the average values for the random subsample of group B, and this is the difference. So I compute a difference between the two average values and then return it. This is exactly how, for example, t-test does, right? So what t-test does, it also computes a difference of means. And also Toki test, it also computes difference of means. So this is my bootstrap way to compute confidence interval for the difference of means without knowing the theoretical distribution. If you replace mean with median, then you will compute difference of median values. So without any theoretical distribution, you can compute confidence interval for the median working time without recharging the battery. The rest is the same. You simply provide your data frame here. You simply specify this function that you have here, number of values, number of iterations, and then the rest is the same. It's only the function and the data set which are different. Okay. So let me show you again how it works in the RStudio. So I will simply continue my script here. So I create A is a vector of all these my values for sample A, 13.1. I use the same values as I showed you before in my slides. Then I create also the values for my sample B. So this is my new 2 samples, which I want to compare. Then I combine them together, A and B. So you can see that, for example, in A, I have these values, in B, I have these values. In X, I have a combination. I merge them together. Then I create a variable G, which will tell me which values are from A, which values are from B. Rep B 7 times, right? And then I combine this together to a data frame. So that will be 2 columns of my data frame, X and G, right? A data frame, not data frames. Let's see, like this. And then this is my data frame. So you can see that indeed the first 7 values are from A and the second 7 values are from B, right? Now I can make this function. I say boot Again, you can call it whatever you want. It doesn't matter to call it like this, but I will call it diff mean. So it says that it's difference for means based for bootstrapping function, 2 arguments, data and indices, right? And then first of all, we make a subset of the rows from data, but I will take only first column. So that will be my values. Then I make a subset for G, right? There are several ways to solve this. Not my way is quite verbose, but it actually, I think it's a little bit more clear, right? And then I say data, I say compute average of X, but not all X values, only where corresponding G is equal to A. So I compute the average of subset for A, sample A. Then I do the same for sample B. And then I return the difference, MA minus MB. Okay. So again, I need to load this to my environment. You can see it's here, right? And now we can make a bootstrapping. So we say object equal to boot, then my data frame, then the statistic, boot mean, boot. It's a function that calculates statistic, boot mean, and then how many times, for example, 10,000 times, so how many iterations, right? So let me see. Probably I made a mistake. Let's check it. Boot diff mean, of course. Yes. So now I can show you the histogram. So let me show you histogram, object T. And remember, it's a difference of means, right? So it's not a mean, but difference of means. And then you can see that most of the time the difference was between 0.5 to 1. Sometimes very little it was negative. Most of the time it was positive. So I believe that there is a significant difference between these two means. So I can calculate the confidence interval, object CI, not object, of course, boot CI, our object with bootstrapping results, then the 0.95 confidence, and then type equal to BCA, right? And then you can see this is the result. So this is the confidence interval with 95% confidence, the true difference of means for the whole populations. For these two populations, it's between 0.2 and 2.1. So in this case, we can claim that there is a significant difference, at least at this level of confidence. There is a significant difference between working time in sample A and working time in sample B. And then, as I said, you can also compute, for example, median, right? So you can compute median. I will not change the function name just to make it fast. Median. And then it will also do the same for the median values, right? And then you can see that for the median values, you don't see a significant difference because average values, they are affected by outliers, while median are quite stable to outliers, right? And then if you, for example, make a box plot for these two, A and B, right? You can see that indeed there is a small difference here, right? But because the variation is also very large, so it at least the bootstrapping doesn't find this difference as a significant one, right? So in this case, we cannot see an evidence that there is a significant difference between the median values, right? Then you can see why the mean is significant, because you can see this is an outlier that pulls the mean of the second sample down, right? And then this is an outlier that pulls the mean of this first sample up. So the difference of means will be much larger than the difference of medians in this case because of these two outliers. And that's why we see this difference as significant if we use means, but if we use the statistic which is robust to outliers, median values, we don't see this difference as significant. Okay. So that's how it works. Now let me again back to the slides. So that's it actually about the bootstrapping and about the whole learning sequence. Let me conclude. Well, you have learned a new set of methods. It's non-parametric methods that are based on different statistics calculated for ranks instead of values. So ranks are stable to outliers. Ranks also are more robust comparing to the original values if we talk about some, for example, skewness and other issues in distribution. So from that point of view, it's a good set of methods to have in your toolbox. And then we know that they are simple. We could calculate all these statistics just manually, and they do not require any specific distribution from your data, right? However, there are also many drawbacks of these non-parametric methods. First of all, they require large sample size, right? So you need at least 20 values in most of the time in order to get reliable results. And then they also In general, the power of this sample, the power of these methods is smaller than the power of parametric analogs, or parametric counterparts. So it means that if you want to say the same size of effect, you need to have larger, much larger, sometimes sample size. From that point of view, I always recommend you to use parametric methods if your data quality is good enough to use parametric approach, and only if it's not, then you can use, of course, the non-parametric methods. Okay. And then this learning sequence concludes also the whole course, but you should remember this is a very, very basic course. It gives you only the fundamentals of applied statistics. There are many other methods you can still discover. For example, there is a completely new world which is called Bayesian statistics, which is quite different to what we have learned in this course, because it's just a slightly different, quite different, not slightly, approach to calculate, to make an inference and to calculate all these models and so on and so forth. Highly recommend you to read about Bayesian statistics. There are also more advanced methods. For example, we learned only multiple linear regression, right? But there are many other ways to make regression. So you can make what is called generalized regression, assuming that errors are distributed in different ways. You can use Poisson distribution if your values are, for example, counts, discrete values. You can use any other distribution for your errors and make also quite reliable regression models. You can also learn how to make models with mixed effects and so on and so forth. So statistics is still a big thing. You still need to learn a lot, but this course covers the fundamentals, which in most of the time, 95% of the time, this is more than enough to for example, design your experiment and analyze your experimental results.